Welcome to the course on material selection in mechanical design. We are in module 3 now, and now our focus will be lightweight designs. Okay? So, whenever we talk about weight, what comes in our mind always is the density, right. So, lightweight designs focus will be always how to reduce the density. Now, when you are reducing the density, you cannot unilaterally only reduce the density, because a material has many structural functions to sort of satisfy. Let us say you are thinking of a beam. Okay. So, we are thinking of a beam, I am just drawing a beam here. Okay. Now, I can make this beam as lightweight as possible, okay, by choosing possibly the lightest material, but still the beam has to support some loading, right, some in the form of some force and some moments. Now, if it has to support all these things, then structurally also it should be able to be strong enough to support this load, so that the deformation is not very high, so that it does not actually collapse. So, this point then becomes important. That means, you can make it lightweight as long as its basic functional properties are not compromised, and that is what means specific properties. That means, say the modulus of elasticity, not only just the modulus of elasticity is important to check the deformation of the system, but it is the specific modulus of elasticity, something like E over rho or square root of E over rho, or whatever is the material index. It is always to be weighted with respect to the density. So, that is what is the specific properties that we will talk about. So, density, then the specific property, and that will be the key thing that we are going to look into this week in terms of the lightweight designs. Well, so I have already earlier discussed with you all these major important mechanical properties, right, like elastic properties for stiffness control design. So, now when it will be a specific property, it will no longer be E, but it will be something like E by rho or G by rho or K by rho, okay, etc. So, that we have to keep in our mind, and gradually we will build towards that direction. But first and foremost, let us think of the density, forgetting about all other things, that what is it that controls the density of a material. We should be always aware of that point. Now, the moment we will ask this question, and then you will start to look around all the materials, then most of the functional materials are of metallic category. Okay. Later on we will talk about composites, which are today exactly of similar capacity, if not more, but for the metals their density comes because of their crystal structure. That is why I said that role of crystal structure needs to be understood if we have to understand that what is the source of density in a metal. Now, the thing that then we have to keep in our mind is that how do atoms assemble into solid structures, and when do material properties vary with sample or orientation, and how does density depend on the structure. Okay. So, that is what we are trying to figure it out, because that will give us some clue in terms of our material selection. Well, now this topic, if we think of it from the metallic systems point of view, it is enormously connected with a classical field of physics called crystallography. Okay. So, crystallography essentially studies the atomic and the molecular structures. Now, the study of crystal geometry helps us to understand that how the atoms in a material are arranged. First of all, whether there is any orderliness in it at all. If there is an orderliness, then in what pattern. So, that will help us to interpret the relationship between atomic structure and properties. These properties may be mechanical, electrical, magnetic, optical, metallurgical, and mostly we will first look into the mechanical properties in our discussions. Now, one common technique which actually is used in terms of understanding the presence of such ordered structure, molecular structure, is through XRD, which is the abbreviation of something which is called X-ray diffraction. It is a very popular technique today. I will just show you a small video courtesy the Center on Materials and Devices for Information Technology Research, University of Washington and Smith's detection, that how an X-ray diffraction works. If you look at it, that X-rays are transmitted at different angles, okay, and at different wavelengths, okay, and through that we try to see that with respect to the change in the spacing as these waves are hitting, if there is any periodic structure present in the crystal or in the lattice or in a metallic system, then what is that order of periodicity? Because as you know that each one of these X-rays that are hitting these atomic systems, okay, so they are reflecting some part back of it, and the same thing is happening from all the nearby sources. So, there is inevitably a constructive and destructive interference happening, and then that is going to give us an idea about the spacing of the atoms in the crystal structure. Okay. So, that is what we try to figure it out, and it is not only us as mechanical designer we try to figure it out. Interestingly, the people in the safety devices, every time we actually send our luggages in the airport, it actually goes through the same scanning system where people actually send these incident X-rays and look into the diffracted X-rays, and which is based on the Bragg's law, and then they try to figure out that whether there is any orderliness present in the structure or not, and if it is not, if it is a polymer, whether that polymer has any explosive elements present in it or not. So, that is something that is so crucial for our safety also. Now, in terms of the arrangement or order, any solid material can be actually sort of divided into three categories: crystalline, which means the entire solid state is in a single pattern. Okay. Polycrystalline, which means there are patterns, but they are locally distributed by the grain boundaries, for example. So, then it is a polycrystalline. And amorphous, which means it is completely random, there is no pattern in it. So, we can in fact say that many times this actually varies between 100% crystalline to 100% amorphous, and most of the times the material can be say 60% crystalline, 40% amorphous, like that. So, it need not be completely crystalline and it need not be completely amorphous also. Many times the materials will be in between the two. Now, when we are talking about the crystalline solids, then we are always talking about that there has to be a sort of a large range arrangement in the system, which is a regular orderly pattern, and such that we can actually describe it in terms of repetitive unit cells. Now, one of the plus point of it is that the crystal structure will show high degree of anisotropy. You may consider it plus, you may consider it minus. The plus point is because in one direction it will be extremely strong and in another direction it may be very weak. So, we have to orient this crystal towards the direction where maximum load is going to come into the system. So, in that sense anisotropy will be of help for us. The other interesting thing of a crystalline solid is that it has a sharp melting point. That means, at a particular temperature suddenly all the arrangements is going to get lost, and there are many metallic elements that are best examples of such kind of a thing happening in the system. Now, in a crystalline structure you may have a single crystal that means which is having only one grain, there is no grain boundary, and that you can obtain if you can completely control the cooling process of a liquid material. Okay. So, you have to do this cooling very slowly, allowing the material to form these kind of a sort of a highly ordered structure. Okay. If you cool the material very fast, then even for a metal it will become glassy or amorphous, because if you take the temperature very fast out, then it will not be able to actually form this ordered pattern. That is why the cooling rate plays a very important role in the crystal formation. Now, this also you have to keep in mind that this also has to happen in throughout the entire volume of the material. Okay? And that is why when we actually make these metals to be glassy or amorphous. So, amorphous metal. Okay? That is a very interesting thing. We always think glass means ceramics, but metals can also become glass. Okay? So, then amorphous metals like bulk metallic glass. I will talk about such a system, and this is or BMG. Okay. So, this is almost fully sort of glassy in nature, and it is amorphous, that means there will be in that metal there will be no crystal structure present in it. Okay. What will be the advantage of such a system? That it will be much more isotropic than these single crystal and isotropic systems, and that would mean that if there is a function on an application, let us say like something like a hydrostatic pressure. Okay. So, the force is coming from all around, a bulk metallic glass will be able to resist that kind of a system much better, whereas an anisotropic system is always strong in one direction, but weak in the other direction. Now, so for one of the tricks, and that is why developing bulk metallic glass is so difficult, is that you have to cool it all around, and no matter whatever you try to do, there will be materials inside that molten metal where it has a locally surrounded by a hot environment, and taking out that is very difficult. And that is why beyond a certain thickness, you cannot create the bulk metallic glass, because you cannot conduct the heat out from inside points of the metal. So, its thickness is very limited today. Well, now the other important point is that if you have multiple grains, okay, then one of the thing that can happen is that this creep resistance, okay, that the resistance to high temperature deformation, that will be smaller, because there will be grain boundary sliding as you are increasing the temperature. Whereas, for a single crystal, that problem will not be there, because the entire crystal is having a single grain itself. And that is why nickel based super alloy gas turbine blades, they are invariably made of single crystal systems. Now, making single crystal, as I told you, is a very challenging thing, because you have to control the cooling rate. Okay? And hence, one of the extreme example is, for example, the diamonds or the semiconductors, etc. Okay? And you can see here that the type of anisotropy that may develop. Say, for example, this is a BCC iron, that means body centered crystal cubic structure, and you can see that this center there is an iron atom, and because of this, in the diagonal direction you have too many iron atoms. So, it has a high modulus of elasticity, something like 272 gigapascal, whereas in any other plane like these x, y planes, etc., the H planes, it is 125 gigapascal. So, that shows that what is the degree of anisotropy that can happen because of a entirely crystalline structure. Now, then naturally polycrystalline solids are desirable in certain cases, and in this case it will be an aggregate of many single crystals, and each are defined by its typical grain boundaries, as you can see here, that here these are the arrangement directions, whereas here the crystal arrangement directions is something else. And so, across the grain boundary the orientation of the crystal is changing, and the grains are between say 100 nanometer to 100 microns. So, there is a large variability possible in it. Now, polycrystalline materials have a higher degree of order over many atomic or molecular dimensions, and with grains less than 10 nanometer, if we can develop polycrystal, that is very challenging, then it is called a nanocrystalline material. Okay. Now, these materials may or may not vary their properties with the direction. In many cases you can actually achieve isotropy. In some cases, if the grains are textured due to rolling for example, then it becomes anisotropic. So, that is why what manufacturing process you are taking in order for the same material, whether you are using rolling or not, whether you are texturing it, whether you are allowing the grains to go in a particular direction, the strength will change. Okay. So, one has to and the modulus of elasticity also. So, for a steel for example, about sort of isotropy will give you 210 gigapascal, okay, whereas this can vary a lot. Now, of course, the extreme example is amorphousness. That means the atoms are completely disarranged with respect to each other and they are irregular. So, there is no periodicity in the packing, no directional properties. Okay. So, this happens if you are having a complex structure. For example, most of these organic materials are having complex structures, or as I told you, if you are rapidly cooling from the liquid phase. So, the glass, polymers or plastics, rubbers etc., this belongs to this kind of a category. Sometimes, for example, for a polymer, I can tell you that it can be completely irregular most of the parts. So, that means it is amorphous, but there are certain local regions where there will be a high degree of periodicity. Okay. So, this will be locally crystalline. Okay. So, there are some such examples, sometimes this forms in the form of a wheel also. Okay. So, this is called spherulite. Okay. So, this is a typical example where a polymer shows amorphous nature all around except at the cores where they are going to have some kind of a periodicity. So, now we have noted down that there are different types of packing. There can be single crystal system and there can be polycrystalline system, there can be amorphous system. Now, interestingly, we have to keep always in our mind that density is a kind of is a function of, you can say, packing multiplied by the weight of the atoms, okay, atomic weight, right. So, you see that if a material has a high degree of order or crystallinity, then the packing is very compact. Okay. So, then it has a possibility of having higher density. Also, if it is having materials, the atoms of higher atomic weight, okay, then also it is going to show higher density. Okay. So, that is why if you compare this metal and then you keep the ceramics and then you keep the polymer, okay, and then compare them in terms of atomic weight. Okay. Metals are invariably having very high atomic weight. Okay. So, this will be very high. Ceramics atomic weight will be moderately high. Okay. So, moderate. Polymers are mostly consisting of carbon hydrogen type of chains, and they are all very light atoms. Okay. So, for polymers the atomic weight will be very light. Now, if you think of the packing, for metals the packing will be very high. For ceramics the packing is high. Okay. They are also crystalline, they are also regular in nature. Okay. May not be as regular as the metals, but they are also quite regular in nature. But for the polymers it is very poor packing, because there is almost no crystallinity there. So, what happens then? If I look at density, which is the product of the two, then for metals both atomic weight and packing is very high. So, that is why metals this thing is density is going to be very high, and this one is moderate, and for this one already the packing is very poor and it also consists of lightweight atoms. So, hence this is very low. So, this is something that we have to keep in our mind when we are looking for the materials for our choice of a design. Now, let us look into that how we are going to sort of quantify the crystallinity, okay, of a metallic system. Now, we will invariably look into something which is called the unit cell, and that is nothing but the smallest block of geometrical figure from which the crystal is built up by repetition in 3 dimension. Okay. So, the fundamental grouping of particles which are repeating the entities, that is one part, and then a unit cell is this basic structural unit or building blocks of the crystal structure. So, a crystal structure can be constructed from a unit cell in multiple direction, like if it is in one direction you get actually a unidirectional sort of a bar beam type of a system, right. So, unidirectional crystallinity you can get it in the form of planar system, you can also get it in the form of a 3 dimensional system of packing of unit cells. So, depending on the nature of applications, sometimes you have to go for a planar application like a thin sheet application, sometimes you may have to go for a cubic kind of an application for a bulk property of a system. Now, essentially a unit cell being a 3 dimensional system, there are 6 parameters that are required to define it. Okay. These are the length parameters and the angle parameters, and as it is self evident here that each of them, say for example, x direction A, y direction B, z direction C, and then each one of these angles, like corresponding to x direction, that angle is alpha. Okay. So, that vector turning towards the x direction, and then so that was in the yz plane, then in the xz plane it is beta, and then in the xy plane it is gamma. So, thus you are going to characterize a unit cell by 6 maximum generic unit cell possibilities will be when you are going to have 6 different parameters A, B, C as well as alpha, beta and gamma. Though in reality there will be always some kind of simplification, like A and B could be similar, or all the ABCs could be similar, alpha, beta, gammas are different, or ABCs are dissimilar, but alpha and betas are similar. All these different cases will construct different special group of crystal structure. Now, one important point we have to say in this area is that there are two things, one is called a lattice, another is called a basis. Okay. So, lattice is essentially the arrays of points in space, like you can see that these are the lattice, okay, in which every point has identical environment with respect to all other points. and basis is the single atom or a group of atoms identical in composition and orientation in space. So, this is the basis. That means, if you apply the basis on a lattice, then you get finally the crystal structure. So, a crystal structure in essence is a combination of the basis plus the lattice. Now, I told you that the lattices can have many different variations. If A, B, C are completely unequal and so too the alpha, beta, gamma, then you get something which is called a triclinic lattice structure. Okay. So, the volume of triclinic lattice structure from the 3D geometry you can actually find it out, which is ABC is square root of 1 minus cos 2 alpha cos 2 beta cos 2 gamma plus 2 cos alpha cos beta cos gamma. Now, you can have a system which is monoclinic, that means A not equals to B not equals to C, but alpha and gamma are perpendicular 90-degree angles, beta is not 90-degree. So, for such a system which is more simple system than the triclinic system, you get a monoclinic system. Then you get something which is orthorhombic, in which all the alpha, beta, gamma are perpendicular 90-degree, but A not equals to B not equals to C. Okay. Some of the materials we handle like shape memory alloys, they come at certain phases, they show this orthorhombic kind of a system. Now, then you can also have rhombohedral tridiagonals. Okay. Here A, B, C will be equal, alpha, beta, gamma will be equal, but not equal to 90-degree. This is a rhombohedral system. And then you can have a cubic system, which is the simplest one. A, B, C are all equal, alpha, beta, gamma equals to 90-degree. Then you can have a tetragonal system. Many of the ceramics follow the tetragonal system. Some of the smart materials are also tetragonal. So, here A and B are equal, but they are not equals to C. That means, in one direction the lattice is slightly more elongated. Alpha, beta, gamma are all equal and equals to 90-degree. That is the tetragonal system. And finally, you can have also a hexagonal system, where A and B are same in a plane, but C direction is longish, alpha and beta are 90-degree, but gamma is 120-degree, and as a result of that you get a hexagonal lattice system. Now, I have sort of kept all of them together in one place, that is where you can sort of keep all these things with you: cubic, hexagonal, tetragonal, rhombohedral, okay, orthorhombic, monoclinic, triclinic. Okay. So, these are some of the basic lattice parameters for the 7 crystal system. We always call it that these are the 7 crystal systems. In nature, some of them are very rare. For example, cubic crystals is quite uncommon. Okay. So, some of them are rare, but some of them are much more you would see frequently observed. Okay. Now, we will also see that they have a very important role in terms of determining the density of a system. So, if we now a few examples, like say simple cubic structure. Okay. So, it is going to have only the it is a cube in which the atoms are only at the corners, at the vertices. Okay. That means, there are 8 atoms. Okay. And how many ways one atom can be shared? Well, you see, this atom can be shared with one definitely like this, okay, on that same plane, right, and then it can be shared with another on the same plane. Okay. So, these two are there, and like that in all the directions, right, like this direction 1, 2 such sets, this direction 2 such, okay, these 2 such and these 2 such. That means, 2 into 2 into 2 into 2. So, 2 it is that means 2 plus 2 plus 2 plus 2. So, that means, it will be 8 possible variants in which it is shared. Okay. So, 8 8 direction sharing, and that means, in terms of a single lattice like this, a simple cube, each atom gets only 1/8 share. the other lattices share the other parts of it. Okay. So, that is one important point for 8 corner atoms. Okay. And another important point is the coordination number. Coordination number talks only about the number of atoms surrounding a central atom in a crystal. Okay. So, in this case, if you look at it, that there will be right and left like that in one direction x, same in y direction and same in z direction, right. So, 3 directions. So, that means you are going to have 6 as your coordination number. Okay. And as I told you that this is something which has a very poor packing and it is rare, available for example, in materials like polonium. Now, one important thing we have to always calculate is that how many number of atoms are there per unit cell. So, we saw that there are 8 atoms here and each atom is shared 1/8 because they are corner atoms. So, n is 1/8 into 8, that is 1. Now, then what is my atomic packing factor? That is atoms per unit cell and then volume per atom divided by the A cube is the cube's volume. And if you approximately consider each atom to be spherical in nature, you can calculate it now, and that A will cancel from numerator and denominator and the atomic packing factor will come out as 0.52. So, which means if you have a SCC structure, you only get 50% of the space of the lattice occupied, rest 48% is void. That means it will be very lightweight in nature. Similar calculations you can do for a BCC. Now, you can understand that for a BCC, it will be 1/8 times 8 plus 1, there is 1 at the center which is not shared. So, it will be 2 and hence you will get a packing factor which will be 0.68. This is a much better packing factor, 68% of space is occupied and also by heavy atoms such as chromium, iron, molybdenum, and some light like potassium, sodium, then again tantalum and then the vanadium. So, this is a BCC structure. And if you go for FCC, that means now it is 1/8 8 into 8 plus you have the halves at all the face centers. So, you are going to have 6 of these halves and then it will be 4 and that means this calculation will give you about 74% of the space to be occupied, which is much better than the BCC. So, this is one of the highest in terms of the packing factor, only 26% void is left. Now, if you go for another pattern which is called the HCP or hexagonal close packing structure, and that is something like this AB, AB, AB hexagons in it. It has a coordination number of 12 and here number of atoms per unit cell would become 2. However, here you are going to get this also is different because it is hexagonal in nature. So, you get the packing factor to be 0.74. Magnesium, cobalt, zirconium, titanium, okay. Some of them cobalt, zirconium, titanium, magnesium, invariably we use them as structural material. 74% of packing helps us a lot. Okay. So, you see that this is 74% HCP and 74% of the FCC and then 68% of BCC. Okay. So, these are some of the things that we have to keep in our mind. Now, you will see that how they play an important role in the determination of density, because density I told you will have a number of atoms per unit cell and the atomic weight, okay, and then volume of unit cell and then the Avogadro number. Of course, Avogadro number you cannot change and what you can play with, you can have more number of atoms per unit cell. You can choose the materials with lighter atomic weight, because if they are of higher atomic weight, invariably they will be of high weight, high density, and also volume per unit cell. So, we can do one such calculation. Say if I choose copper, crystal structure of copper is FCC, that means 4 atoms per unit. Atomic weight of copper 63.55 gram per mole. Atomic radius of copper 0.128 nanometer, from which you can actually calculate the Vc, and then you get a theoretical density of 8.89 gram per centimeter cube. In fact, if you measure the density of copper, it will come out to be 8.94. So, it is like the way we do it makes lot of sense. Okay. So, this gives us a clue in terms of the choice of material in terms of its crystal structure. And as I told you that always invariably, because of the close packing and large atomic masses, density of metals will be higher, in between will be ceramics, and the lowest will be the polymers. Composites can have average values because you are having some ceramics as a fiber, let us say, and some polymers. So, it is going to be slightly lower than the ceramics, but slightly higher than the polymers. So, that is the way it will be. In terms of density, then no wonder that except possibly aluminum, beryllium you can rule it out because it is very corrosive in nature. So, aluminum, and the next good is titanium. Okay. And in terms of the density of ceramics, it is the glass, cements, etc. And in terms of the density of polymers, the highest will be of similar order, that is polytetrafluoroethylene, PTFE, and most of them are much lower, as you can see here. And in terms of composites, it can go anywhere towards comparable density up to silver level, let us say. Okay. And however, mostly you will see it in this region where it is comparable to the lighter metals like aluminum, but having a much higher strength. So, this is the important part in terms of our material selection. In the next lecture, I will do a little bit more in terms of the significance of crystal structure. Thank you.